Hello, everyone. Welcome to Physics Lab. So this is Lab 2 for Physics 212, and it's on the addition of vector quantities. In particular, we're going to be adding force vectors together. We're going to be adding them together two different ways, experimentally and also graphically using a protractor and ruler. This is also Lab 3 for Physics 206 and 207. And it's very similar. It's just that the different labs have to do different parts of this. But instead of being redundant and making 3 separate videos, I'm just going to make one video and I'll indicate which parts each section has to do or which each course has to do. Okay, so the first part is the theory. I already talked about this. Make sure you watch that other video on how to add vectors together. So we've discussed this. Now for the experiment, and for this first part, all 3 labs have to do this. So Physics 206, 207, and 212. What we're going to do is we're going to add 2 vectors together using a Kennen force platform. Now, I created another video where I show you how I actually add vectors, how you read that Kennen force platform, and how you use it to add 2 force vectors together. So make sure you watch that. It's hard to explain it in words, but if you watch that video, it'll make sense. So basically, we're hanging 100 grams, right? 100-gram load on one of the hangers at 30 degrees and a 200-gram load at 120 degrees. And then using the third pulley and the third hanger, we're finding the position of that pulley and how much mass we have to put on the hanger, so both the position and magnitude, such that the entire system balances. And by doing that, we're finding what's called the equilibrant force. And that's going to be equal in magnitude to the resultant force, which is what we really want because we're adding 2 force vectors together to get us a resultant vector. But the direction of the resultant is exactly opposite that of the equilibrant. So once we read off the direction of the equilibrant, then we can subtract 180 degrees to get the direction of the resultant force. So I gave you a table here. And again, if you're watching this because you missed lab, most of this will be explained in lab. If you missed lab, then you need to get this data from your lab partners. If for some reason you can't, contact me and I will give you some data that you can work with. Okay, so again, we have 2 masses, right? 100 grams at 30 degrees, mass 2 is 200 grams at 120. This is the equilibrant. We had to figure out what that mass was. So once you do the experiment, you'll know that value and we'll know the angle of the equilibrant. If we want the resultant vector, then the mass doesn't change. Whatever that mass is, it's going to be the same. But the direction, we have to subtract 180 degrees from the direction of the equilibrant. So for example, if the equilibrant was at 270, then the resultant, which is what I want here, is going to be 270 minus 180, which is 90 degrees, right? It's the exact opposite direction. So the first thing that you should do is you should fill in the last column of this table here. And what you need to do is, given the mass, you need to compute the force in newtons. So given the mass in grams, so for force 1, for force 2, and then for the resultant, we need to compute the force in newtons. Okay, let me show you how to do that on the iPad. Okay, so it turns out that the tension in the string, which is the force that we're interested in, F1, F2, and then resultant, is really, in this case, it's equal to the weight of the hanger plus the masses that are placed on it. So how do we calculate the weight if we know a mass? Well, we know that the weight is equal to the mass times the acceleration due to gravity, which is a constant. But we have to be careful here. If we want to know the weight in newtons, we have to make sure everything's in the correct units. So the mass has to be in kilograms. And then G is going to end up being 9.8 meters per second squared. So G is always the same. That's just a constant. So for example, right, if F1 was 100 grams, we want to convert that to newtons. So we have to multiply. First of all, I have to convert from grams to kilograms. How do I do that? Well, I know that there's 1,000 grams in 1 kilogram. So I can use a unit conversion factor. I can multiply by 1 kilogram over 1,000 grams. So now if I stop there, right, grams will cancel. That'll give me kilograms. And now if I multiply by 9.8 meters per second squared, that gives me what I want. If you work this out, you're going to find it's 0.98 newtons. So you want to do that for all three forces, for F1, for F2, and for your resultant force. I'll call R experimental. So you want to do those conversions for all three forces. Okay, then the first question that you're responsible for is question 1 from the lab manual. If you're in Physics 206, actually this is written out on your handout. You don't have to worry about lab manual. If you're in Physics 207 or 212, then the questions come from the lab manual. So question 1 wants you to sketch the 3 vectors, F1, F2, and R. So I basically did the sketch here, but let me show you this on the iPad as well, what you need to do for this question. So the best way to do this is probably just use graph paper, right? So on your graph paper, you're simply going to do a sketch. So this doesn't have to be drawn to scale. It's just a sketch. So remember F1. So if this is like x-axis, this is y-axis. It was, you want to label it in newtons, right? So it's 0.98 newtons. And the angle was 30 degrees. Then F2 was whatever it is in newtons, right? You have to convert from grams to newtons. And then the angle here was 120 degrees. And then it depends on what you got for your equilibrant. That's going to determine what your resultant vector is, like what direction is, what the magnitude is. Let's say your equilibrant, I'll do this in red. Let's say on the Cannon Force platform, it was in this direction. Let's say it was, I don't know, 230 grams. And let's say it was at 271 degrees. So on the sketch, you don't want to sketch, this would be the equilibrant. You don't want to sketch the equilibrant. You want to sketch your resultant vector. So what direction is your resultant vector? So for the resultant, which I'll call R, actually I'll call R experimental. How do we find a direction? Well, it would be 271, right? It's a direction of the equilibrant minus 180. Minus 180. And that would be 91 degrees in this case. And then how would you find the magnitude in newtons? You'd have to convert the 230 grams into newtons. So in this case, it would be like in this direction. So that would be R experimental. And you could label it in newtons, and then you could label this angle, I'll call it theta experimental. This was 91 degrees. Okay, so it's just a sketch, right? But you want to make sure that you label everything. So label, I'll say label forces in newtons and label the angles. You're always going to do that on all your diagrams. So you have 3 vectors, F1, F2, and R experimental, and you label the forces, however many newtons they are, and you label all the angles. Okay, and I would actually show these conversions. So again, I did one for you earlier. right? If this is 100 grams times 1 kilogram over 1,000 grams times 9.8 meters per second squared, that's going to be 0.98 newtons. Then show it for F2, which is 200 grams. And then whatever you guys got for our experimental, I just made up a value, say 230. So you're going to show those calculations, right, for all three. And you can just do this all in the graph paper. All right, so that's question one. That's a sketch. Question two is really the same as question one. It's going to look the same, except these vectors are going to be drawn to scale now. So now you're going to use a protractor and ruler and do this nicely to scale. Okay, so again, this is question one. Let me go to new page and talk about question two. So again, it'll look the same, except it'll look a lot nicer now. Right, you're going to label everything again. But now it's all going to be nicely drawn to scale. I don't know what these are, so I'll just leave it as blank newtons. And whatever you got for the angle. Again, I made up that value. I got 91 degrees. You may get something different. You might get 93, 94, 90, whatever it is. Okay, so how do you figure out? So the angle is easy, right? The angle you can just use using a protractor. How do you figure out how long to draw it? Well, we're going to use a conversion factor. We're going to say that, let me do this one right here. 5 centimeters, you want to use this one, is equal to 1 Newton. So for example, F1, which was 0.98 newtons. If I want to figure out how long to draw, I need to multiply by 5 centimeters over 1 Newton. Right? It's a unit conversion factor. The newtons will cancel. If you multiply 0.98 times 5, we're going to get 4.9 centimeters. So when you draw this with a ruler, you're going to draw the length of that vector 4.9 centimeters long. But when you label it, make sure you label it in newtons. It's still 0.98 newtons. And then the angle you just get from a protractor. Okay, so that's question two. The next question that you're responsible is question three. And question three is a different way of adding these two vectors, F1 and F2 together. Remember, this information that we just found here, this comes from the Kennen Force platform, right? We got this by adding these two vectors experimentally using the Kennen Force platform. Question three, now we want to add vectors F1 and F2 graphically using the triangle method. So again, I'll go to a new page here. So how do we do that? Well, you're going to have a coordinate system. You want to draw this to scale, so it has to be done nicely with a protractor and ruler. Again, you're going to use 5 centimeters is equal to 1 Newton. And remember, to add them graphically using triangle method, you have to first draw F1 where it's tails at the origin. So that'll look the same. You should label it in newtons and label the angle here. And then we're going to put a new coordinate system at the tip of F1. And then F2 will start at the tip of F1, right? The tail of F2 is at the tip of F1. Let's say it does this. So now we have F2. We know how many newtons that is, so you can label it. And you know this angle, I'll just label it here. Remember, this is 120 degrees. And then how do I find the resultant vector? The one, you don't make the mistake of trying to draw the one that you already calculated experimentally. You're actually going to find it just by connecting, right? In this case, once we've drawn F1 and F2, all you have to do now is connect the tail of F1, so from the origin, to the tip of F2, like this. And that's going to be your resultant vector. And to denote that it's different, I'll call it our graph. Now, how do we get the magnitude? Well, you can measure the length of this, right? So you measure the length of that vector. It's on your graph paper. And you convert back to newtons, right? Let's say it's, I don't know, let's say it's 11 centimeters long. Then if you multiply by 1/5 or divide by 5, that'll give you back to newtons. Okay, so you're going to measure it and convert back to newtons. And then how do we find the angle? You're simply going to measure this angle with the protractor. And I'll call that theta graph. So now we found R graphically, and then we found it previously experimentally using the Kennen force platform. Right, so we found R using two different methods. Okay, next. Okay, so we have our results from the Kennen force platform, right? Our experimental magnitude and direction of our resultant vector. We have our results from the graphical method, the triangle method, right? So we have our graph and also the magnitude and also the direction, theta graph. Now we want to compare those. We want to compare the magnitudes and compare the direction. So this is question 5. We're not going to do question 4, so that's why we're skipping 4. So we're going to question 5 from the lab manual and simply ask you to compare the magnitude and direction. So I gave you a little table here, and just a reminder, remember to compute a percent experimental error. It's going to be your experimental value of R, right, however many newtons that is, minus the graphical value of R, however many newtons that is, absolute value, divided by the graphical value. We're considering the graphical to be like our accepted gold standard value today. So it's experimental minus the accepted gold standard divided by the gold standard times 100, right? And absolute value just makes it positive. And then do the same thing with the error. Compare the angles. So your experimental angle, 91 degrees. Then whatever you got graphically, when you measure a protractor, let's say 92, it'd be 91 minus 92, absolute values would be 1 divided by 92. You want to use your graphical as your accepted value times 100. And then those answers go in the table here. Okay, great. So if you're in physics 206, that's all you need to do. You can stop watching this video. If you're in physics 207 and 212, then we're going to do more parts. The second part actually is only going to be done by physics 212. Okay, so let me describe this. So now you're going to hang 400 grams at 0 degrees in the Kennen force platform and 300 grams at 90 degrees. And then fill in this table. So you're going to balance it, right, using the equilibrant. And then we really want the resultant vector. So you're going to have the magnitude, whatever you had to hang on it to balance it. And then direction, you have to measure the direction of the equilibrant and subtract 180 degrees. And that'll be the direction of the resultant. And then make sure you show me these 3 force calculations where you compute the force given the fact that the mass is 400 grams, 300 grams, and whatever you get for the equilibrant, right, for the resultant. Okay, then there's just 2 questions for this part. Again, only 212, physics 212 needs to do this part. Question 6 is similar to question 1. It's just a sketch of this situation. Okay, so let me jump over to the iPad to show you actually these 2 questions, 6 and 7. Okay, so again, question 6 is just like question 1, just a sketch. So here's our coordinate system. Remember, F1 is at 0 degrees, right? So that's going to be right along the x-axis. Make sure you label it, whatever it is in newtons. And then F2 was at 90 degrees, right? So this is 90 degrees. So it's right along the y-axis and whatever that is in newtons. And then the equilibrant, right? Remember, it probably balanced over here somewhere. And you know that mass, so you can convert that to newtons, you know the magnitude. And then direction, you had to subtract 180. So then you know that the the resultant is actually in the opposite direction. So it's going to look like, let's say it looks like this. So this would be our experimental, and then whatever that is in newtons, and then whatever you got for the angle here. Okay, so it's just a sketch, right? This is question 6. Okay, question 7 is you're drawing this to scale, but you want to use 3 centimeters equals 1 Newton as your scale factor, and then you're going to do one more thing after that. So question 7 is you're basically drawing question 6 to scale, but you want to use 3 centimeters is equal to 1 Newton. That'll work out better for this. So again, let's say this is F1, I'll do it in blue. So now it's nicely drawn to scale. Make sure you label it again in newtons, and then you don't have to label 0 degrees, but so that's 0 degrees. And then here we have F2, right? Drawn nicely with a ruler now, the correct length. This is 90 degrees. And then our experimental, let's say it does this. Again, how do you know how long to draw? You have to convert newtons to centimeters, right? Using 3 centimeters is 1 Newton. And then you also want to label this. This is really the experimental angle. Okay, now the last thing you want to do for question 7, if you look on in the lab manual, this is one more thing you want to do. Actually, I drew this a little too long. Let me draw it like this. So there's our experimental. Okay, the last thing you want to do is you want to project onto the axes. You want to take your vector R, your R experimental, and starting at the tip, right, the arrowhead, we're going to draw perpendicular down to the x-axis. Like that, and then a perpendicular over to the y-axis like this. So these are what's called the components. So if this is R, remember this is R experimental. And this would be like R experimental in the X direction, like X component. And then this would be R experimental in the Y direction. So those are the X and Y components of your resultant vector. Now, if everything were perfect, right? If the experiment was done perfectly and there was no errors in measurement, no friction in the Cannon force platform, then what should be true here? Well, remember our original F1, right? Remember this is F1, was right along the x-axis, and our original F2, these are really vectors, it was right along the y-axis. So if everything was done perfectly, then it turns out that the X component of R should equal F1. And the Y component of R, so Rx, the Y direction, that should equal F2. Now, because everything's not perfect as an experiment, you might find these are slightly different, right? There might be some error here and some error here. But in theory, the X component of your resultant vector should equal F1, and the Y component of your resultant vector should equal F2. Okay, and hopefully you'll see that when you do that drawing out. Okay, and then the last part of this lab, part 3, this part, both physics 207 and 212 needs to complete. Basically, all you're doing in this part, this is sort of like part 1, except now you're adding 3 vectors together to get a resultant vector. So actually on the Cannon force platform, you have to use 4 pulleys now, 4 strings and 4 pulleys to add 3 vectors together. So you're basically hanging 100 grams at 20 degrees, 200 grams at 120, and 150 grams at 220. Then the equilibrant, right, you're going to balance it again. You'll know the mass that you had to put on the equilibrant. That's going to be the same as the mass of the resultant. And then to get the direction of the resultant, you have to take the direction of the equilibrant and subtract 180 degrees. And that'll give you the direction of the resultant. And then just like before, you want to show me these calculations. You want to convert or compute the force in newtons given these masses, the 100 grams, 200 grams, 150, and then whatever you got for the equilibrant, right? Show me those computations there, how you got those 4 forces. Okay, in terms of the questions, question 8 is just like question 1. It's just a sketch. You're just sketching these 4 vectors, F1, F2, F3, and R experimental. There is no corresponding question 2, so you don't have to sketch it again, drawn to scale. You're going to go right to the polygon method. So this is basically question 9. And we're going to graphically figure out what the graphically figure out what the resultant vector is. So R graph. And then just like question 5, you're going to compare what you got experimentally to what you got graphically. So that's the end here where you have to compute the percent experimental error. So actually, let me jump over to the iPad one last time and actually sketch this out for you, question 8 and question 9. Okay, so again, question 8 is simply a sketch, just like question 1. But now we have 4 vectors that we need to sketch, right? We have F1. Again, make sure you label it in newtons. This one happens to be 0.98 newtons again. This, I guess, was 20 degrees, right, this time. Then we had F2. Label it in newtons, label the angle. So this is 120. Then F3 was 220. And to get to 220, remember, we always start at the positive x-axis and we measure counterclockwise. So if I go to here, this is 180, and I need to do another 40 degrees, right? Another 40 degrees. So that's in the 3rd quadrant like this. So F3, whatever that was in newtons, this is 220 degrees. And then finally, you're going to sketch R. Remember, the equilibrant is probably in this direction, the 4th quadrant somewhere right here. So you know the amount of mass you had to put on there in grams, so you can calculate the newtons, right? The force in newtons. And then if you subtract 180 degrees, you'll get the direction of the resultant vector. So it's got to be in this direction, right? Something like that. And remember, don't sketch the equilibrant. I just dashed it in so you know if the red's in that direction equilibrant. You just want to sketch the resultant. So this would be like R experimental, whatever that is, newtons, and then you can measure this angle because you know the equilibrant minus 180, that'll give you theta experimental. Okay, and again, just like before, show the 4 computations from grams to newtons. Right, so show them for each force. F1 was 100 grams, so that one's going to be the same, right? 1 kilogram over 1,000 grams times 9.8 meters per second squared. That's going to be 0.98 newtons. Then show it for F2, show it for F3, and then show it for R experimental. Show me those 4 conversions now, or 4 computations. Okay, that's question 8. Question 9 is now we're going to, so again, there is no like corresponding question 2. You don't have to draw this nice and neatly using a protractor ruler, just sketch it, right? All the vectors are coming from the origin. But question 9 is adding these 3 vectors now using polygon method. So again, it's nothing more than what we did earlier, but you just continually add tip to tail. So if this is my coordinate system, you start with F1. Make sure you label everything again. Then from F1, I'm going to draw F2, let's say it does that. I'm going to label it in newtons. I'm going to label this angle 120 degrees. And then from F2, I'll draw a new coordinate system. Now I have F3. Remember, F3 is going to be 220 degrees. So I have to go 180 and another 40. So you kind of have to flip your protractor over and go another 40 degrees. Let's say it looks like this. So this would be F3, whatever that is in newtons. This angle right here is 220 degrees. And then finally, to get our graph, I connect now the tail of F1, so from the origin to the tip of F3. So this is our graph. How do I figure out the newtons? Well, I would measure the length of this, and then using the same conversion factor, again, we're back to 5 centimeters equals 1 Newton. I can divide by 5 and convert this to newtons. And then to measure the angle, I simply use the protractor. So I'll call this theta graph. And then the last part of question 9 is you again want to compare. You want to compare the magnitudes, our graph, to what you got experimentally, right from here. So our experimental, you're going to compare to our graph, and then you're going to compare the angles. Theta experimental, whatever you got from the Kennen force platform, right? When you subtracted 180 from the equilibrium, you're going to compare that to what you got by the graphical method where you measured it with a protractor. And by comparing them, I mean you're going to compute a percent experimental error. Okay, so go back one last time to the handout. Okay, so again, the last part of question 9, after you do the polygon method or graphical method, is to compare the magnitudes and direction again by computing the percent experimental errors and then record those values in the table here. All right, and then that's it. Although there is an optional question, and this is really for Physics 212. If you have already learned how to add vectors analytically in lecture, I'm not going to cover that in lab right now because we just don't have the time. But if you've already learned how to do this in lecture, what you might want to do is do this last part again. But like, so now that you have the 3 forces and their directions from the table here, you can add these 3 vectors analytically if you know how to do that. So like using sines and cosines and Pythagorean theorem and inverse tangent, if you know how to do all that, then you should try to do that and make sure you get an answer that's pretty similar to what you got experimentally and what you got graphically from question 9. But it's optional. I'm not going to require you guys to do question 10. But if you know how to do them analytically, that's really the best way to add vectors together. Okay, and then you can compare it to what you got experimentally and graphically. All right, and that's it. Actually, to help you out a little bit, I kind of summarize like what you should do for each question because this lab's a little confusing. So I kind of summarized down here what each question from the lab manual wanted you to do. So if you want to look at that again, that might be helpful. All right, so that's it. So that's it for addition of force vectors. Thank you.